Hello, thank you for joining us at the Charge Virtual Conference on EV engineering. The topic of this session is understanding and measuring failure modes in electric motors, brought to you by HBK. There will be a Q&A session after the presentation, so please submit your questions at any time by clicking the Q&A button on your screen. Now, please let me introduce our speaker, Mitch Marks from HBK. Welcome.
All right, I think that's my cue to go. Cool. So yeah, we're going to be talking about understanding and measuring failure modes in electric motors. This was inspired by a couple of papers that came out within the last year and PhD dissertations and just kind of general interest in the industry. So I hope you find it useful. So for agenda, we're going to start off with what are some of the main failure modes in electric motors, and really do a dive into kind of more of the fundamental backgrounds. We're going to look at what are some of the challenges in measuring failure modes and durability, because it's not always straightforward. We're going to look at how we can use electrical signals for monitoring and characterization of these failure modes. And then we're going to go through a little example where you'll find out why I was taking a lighter to a motor rotor. This is my hand. This is a lighter. That is a rotor. So please stick around and find out why. So we'll jump in. So let's start with kind of just a motor construction. This will be definitely background and already known for a lot of you, but I think for some of you, it might be a new topic. So in the motor, we only have a handful of components. We have a stator that has laminated steel that's pressed together. In that laminated steel, we have a series of windings, and we can see that these rotor windings here, so we have these copper windings that are touching each other in many circumstances and going around the machine. We have bearings. That's kind of a failure point. I think would be no surprise. We have rotor hubs, we have steel, we have a rotor that's laminated and pressed together. We have magnets. And we have these permanent magnets that are embedded into those rotor laminations, or if it's an induction machine, maybe we have bars. We have some sort of magnetic on the rotor, and then we have bearing assemblies. And what we see is we really don't have that many components. We have pressed steel, we have copper windings, we have magnets, and we have bearings. So I think it'll be no surprise to anyone that the points of failures are those laminations being pressed together, those windings rubbing together, those magnets not being magnet enough, and the bearings. So going from there, we'll touch on a few of these different topics. And this is a picture courtesy of General Motors. I think it's pretty public from some of their papers. So if we look at the fault modes coming from what I just discussed, we can kind of break them into two categories, and I actually think there should be a third here. But we can break them into stator faults, where we see short circuits, open circuits, inner turn shorts. This is the windings interacting. And then we also have rotor faults. If we remember, the rotor has those pressed laminations, and then either the bars or the magnets or the magnetic material on the rotor. We break those into electrical, which is a broken cage in an induction machine, broken magnets. This could be chipped on insertion or from some sort of mechanical abuse. And demagnetization, where the magnet becomes weaker than we expect. We also have mechanical failures, eccentricities, misalignments, and bearings. And I almost think bearings could be their own kind of fault on their own. And a study from the EPRI and IEEE kind of breaks down what the percentage of those failures are. Now, this is focused more at industrial machines, but we're seeing very similar trends in EV. There's just less published on it currently. And what we see is that bearings are really a ton of the fault. A lot of those fault conditions are from bearings, and we'll touch on that. We also have stator faults. These are those turn-to-turn shorts. Rotor faults, these are those mostly magnetic issues, and then other, and this is probably forklifts running into things. But we kind of have these three main categories, so we're going to dig into these and look at some of these individually. So let's start with bearing currents. That was, something like 40% of motor failures. And we are seeing that trend kind of continue into the EV space. That distribution is different, but we are seeing quite bearing failures be an issue in the EVs. And there's a reason for that. So what is the fault? Well, one of the bearing faults I'm going to talk today is bearing currents. So we have charge that builds up on the rotor, and this is a cross section of a motor in the picture. We have charge that builds up on the rotor. So basically we have magnetic flux and voltage and electrons that are getting from the stator to the rotor. That charge is building up, and then eventually that charge builds up to a point where it discharges through the bearings to the stator housing. So the cause can be common mode currents, it can be grounding currents, it can be rotor eccentricity, but basically we're getting an electric charge that builds up on the rotor, and then eventually that charge is big enough where that bearing, whether it's a ball bearing, a liquid filled bearing, looks like a conductor, and we get a very fast short circuit through it. So we're actually running a current through that bearing. And over time, that bearing, that ball gets pitted. The fluting of the bearing, or the bearing itself, can get fluted. If it's a fluid bearing, we're going to break down that fluid and it's just going to fault more and more. And eventually this leads to bearing failure because we're making those balls, or we're making those bearings not as round. We're making that raceway not as round. We get more failures, we get more faults, we get more currents. And this can really degrade the life of the bearing and of the machine itself. We can start to get eccentricity, vibrations, all kinds of consequences. And it really is from just charge getting from the stator to the rotor through stray currents, through a number of mechanisms. So bearing currents are a big one. And it is an electrical issue that results in a mechanical failure. So this is introduction one. Voltage builds up on the rotor, releases through the bearings to the stator, and it cooks the bearings. Failure mode two. And again, just kind of giving an overview of these. We'll talk about the measurement in a moment. Turn-to-turn shorts. So many of you have probably seen a circuit diagram of motor, which we have here, which is a three-phase motor, phases A, B, and C with our neutral point at the middle. So what's the fault in a interturn or a turn-to-turn short? Well, the windings are shorted together or shorted to ground. So we can see there's a number of different interturn type shorts where we can have coil to coil, we can have turn to turn. This is two turns that are next to each other that's short. We'd have coil to coil where maybe in the back of the stator they get shorted. We'd have phase to phase. That's quite the exciting failure mode where turns from two phases get shorted together. And if phases are sharing a spot in the slot, this is not unlikely. And then we have coil to ground where maybe the turn shorts to the stator laminations. So it's a breakdown of the winding enamel. So if we have a cooling fluid, it could potentially be a chemical breakdown. If we have mechanical rubbing, if that motor is not secured, a vibration could cause that turn to turn. Or if the enamel gets really hot and it starts to melt, that enamel could melt and two turns could short together. So we have a variety of ways this can happen, and it's quite exciting when it does. So the cause: mechanical stress, electrical stress. We could also see this in the inverter. We could see shorting in the inverter, which would have similar effects. Thermal stresses. And what are our effects? Well, our effects are going to be inefficiency. This graph on the right I included. This is from a dissertation that's in the references, where we see 1% of the winding shorted creates quite a huge fault current. So we can see this just really kind of gigantic fault current just from a very small amount of winding shorting. So we see inefficiency. It can result in demagnetization. And in all honesty, a turn-to-turn short is such a dramatic failure mode that we see really high currents really quickly. And it's ultimately a drastic failure. There are solutions and methodologies for avoiding this. You can sense it very quickly and then do some things in control to avoid this drastic failure. And again, that's kind of featured in the dissertation here, which is, if you're interested in avoiding turn or interturn shorts, an excellent read. But the main takeaway is these conductors on the stator can get shorted together, and they can cause really dramatic currents that result in things like torque ripple, inefficiency, and demagnetization. Lastly, demagnetization. The fault: the magnets lose strength. The magnet shape changes, or we get asymmetrical magnetic characteristics in the air gap. So what is the cause? Well, permanent magnets don't like hot temperatures, which is unfortunate because motors tend to get fairly hot. So this is a BH curve, or a magnetic field intensity versus magnetic flux density. Basically what this says is my magnet likes to operate in this normal region. As it gets more electrical or more magnetic stress put on it, that magnet becomes weaker, but it can recover until a certain point. And if we have too much magnetic field intensity, that magnetic flux starts to dissipate and it cannot recover, and it recovers at a different point. So if you get a magnet too hot, and you put too much current at it, it stops looking like a magnet. And this is due to conflicting magnetic fields, possible stator faults, and is largely driven by heating because this curve changes as it gets hotter. Now, the magnet is really what is the torque producing element in the motor. So the effect of demagnetization, if it's an asymmetrical demagnetization, it can be torque ripple. If it's a symmetrical demagnetization, it can be torque ripple, just different. It can result in a reduction in power, that's the max power output, and it can result in unbalanced line currents. So this is something that we can potentially sense. So these are kind of the faults we're going to go over: bearing currents, turn-to-turn shorts, and demagnetization. And we're going to look at how we can measure these now. So what are some of the challenges in durability testing for electric motors? I wrote this out, but in the long and the short of it, it's really hard to accelerate, because if you start accelerating some of these things, the typical acceleration is we get something really hot and we run it really hot. Well, the high temperatures cause demagnetization, and the high temps drastically alter performance. So we can't really operate the way the machine is supposed to at a really hot temperature. I'm sure we're going to figure some of this out and figure some nice curves for it. But as of now, running an accelerated life test is difficult. And as many of you know, these durability tests run for thousands of hours. So it is difficult when you cannot accelerate. Every motor, and I don't mean motor to motor, I mean kind of design to design, has its own, it's a unique butterfly. They all have kind of their own unique failure modes and characterizations. Different magnet patterns, different winding patterns. Yes, there's general rules of thumb you can follow, but you need to know your machine a little bit to understand how it's going to fail. So, that is one of the challenges. It's not the biggest, but it is a challenge. Rotor temperature is a huge thing for demagnetization, is a huge thing for bearing currents, and it's really difficult to measure. So we need good models for estimation. So we have to do a lot of estimation. It's electromechanical by nature. Electrical influences the mechanical, like our bearing currents. Mechanical influences electrical, like our demagnetization with the magnets getting hot. So we need to understand a lot more measurements. We can't just do temp and torque. We have to do a variety of things now, including electrical measurements. And kind of my favorite thing with durability is we're looking for high-speed events. Like a turn-to-turn short is a super fast failure on a time scale of thousands of hours. So we want to look at how an inverter faults in 1/10 of a second on hundreds and thousands of hours of testing. So this is a fun measurement one where HBK is particularly good at. So I get excited. And the long test durations and how you manage all that data for maybe hundreds or thousands of hours of testing. And HBK does have solutions for that I'll touch on a little later. But these are some of the challenges, the length of some of these durability and fault runs. So using electrical signals for electric motor faults and durability. All right, let's look at the bearing currents. Now this isn't the greatest drawing ever, but it's kind of fundamental. We have our housing, which I'm highlighting now. We have our bearings, which are down here. We have the stator, and then we have a rotor. So one way to measure bearing currents is to just throw a current clamp or a current sensor around all 3 motor leads and look for the common mode currents. If you start seeing unbalanced currents, there's a chance that the source is bearing faults or bearing currents. It's not exact, but it is a good way to monitor for that, especially if you have a well-characterized system. So you just throw a sensor around your 3 leads and you're good to go. You can measure your bearing currents, which is this IB here, which you need to insulate your bearings. Difficult, it's a pain, I know. Run a conductor from the stator bearing or stator to the bearing, and you can physically measure those currents. It's a pain, but you can do it. What is more simple is you can measure the voltage difference you can actually put a slip ring and a high impedance measurement between the stator and the rotor shaft. And granted, you're using a slip ring, so take that for what it is. But you can look at that charge and that voltage buildup and then watch it discharge. So you'll see that voltage buildup, discharge, voltage buildup, discharge. That's probably the way most people are doing it. You can also measure temperatures as the bearing currents happen. It gets hot. So measuring temperature is a leading indicator, and combining temperature with something like VB, the voltage of the bearing between the stator housing and the shaft, you can get a lot of good information. And then, increased frequency or amplitude of the voltages and currents will indicate degradation. So if you're measuring that VB and you see a discharge, every minute, and then you start seeing a discharge every, 30 seconds, relative scale. So just you start seeing that the time between discharge events shorten, that indicates degradation is happening because you're deteriorating those bearings, and now you're just getting more and more shorts. So maybe you go from hours between faults to minutes. Maybe you go from minutes to seconds, whatever your machine indicates. So we have a lot of measurement options, but I think VB and temperatures is probably the best. Measuring inter-turn shorts. This one is fun because when the fault happens, it happens drastically. But how can you know when it's going to happen? What are the leading indicators? And that's where this gets really fun, because you can smell it when it happens because of the smoke and the fire. But you can look at current disturbances, and you can look at the zero sequence voltage. So you do a mathematical transform, which is pretty simple. We can do it in our software to look at what is basically the effective neutral current, and then look at imbalances in that zero sequence. And what I have here is an example of, as we have shorted turns, and the resolution on this is poor, I apologize. As we have shorted turns, we can actually see the amplitude of our zero order spectrum getting higher. And we can actually follow the frequency domain of our zero order and see that our third order, is where everything culminates. We overall see some orders a lot higher for 4 shorted turns than we do 2. So this could be a leading indicator to failure. And for turn-to-turn shorts, that's what we understand, because this is catastrophic. We want to know what leads up to it so we can enter a safe mode. We also look at phase imbalance. If you see the RMS values kind of getting skewed and not being within a certain percentage, that can indicate turn-to-turn shorts. Increases in harmonic amplitude. Again, we can look at the harmonic profile, not just of the zero sequence, but of the phase currents. And certain harmonics will start to peak under conditions of short circuits. So we can look at our harmonic profile, and if we see things creeping away from known values, we can indicate that there's a failure that's going to happen or that has already started. So these are the fun things, is you look for small disturbances in specific areas to understand catastrophic failure. And there's a wide variety of references on this, and I have cited some sources. There's data-driven understanding of what leads to faults, high-frequency injection, if you're in a really fault-prone area. There's model-based determination, digital twin, and then vibration analysis. So there's a number of ways of monitoring, but electrically, you can pick up stuff really quickly before the catastrophic failure. Demagnetization, this one's near and dear to my heart. So demagnetization has a variety of causes: negative d-axis current, flux linkage, stator temperature. So you can monitor these 3 things and know if you're in an area where demagnetization can happen. So if you monitor your negative d-axis current and you're pushing a lot of field weakening, at the same time your stator or rotor temperature are hot, you can know that you might be looking at one of these scenarios. But Demag is kind of, I don't want to say it's convenient to look at, but here is a chart. Again, this is from one of the papers I referenced, of no demagnetization, symmetric demagnetization, and asymmetric demag for 3 different machine geometries. And we look at a variety of things and see how they change in percentage. And there's some things that under a 2% demagnetization, we see a gigantic change in RMS current. Under a 3% demagnetization, we see a 5% change in RMS current. These are things we can monitor really easily. We can look at copper losses, that's harder to measure. Stator core losses, even harder to measure. Magnet loss, extremely hard to measure. These are from modeling. But we look at torque ripple. Torque ripple is a pretty easy thing to measure when you're talking 10 to 13%. That's a big change in torque ripple. these are things we can easily monitor. RMS current is something we can easily monitor. Even copper losses isn't that bad. We can get within 8%. So you can pretty easily determine, in these different machine types, look for demagnetization with the electrical signals. You can predict that, you can see it happening, and you can understand what leads up to it in your fault testing, in your durability testing. And it can also affect losses, average torque, harmonics in the back EMF. Harmonics in the back EMF is a good way to look at magnet shape. Torque ripple is a good way to understand magnet shape. And then reduced back EMF or rotor flux. So I think this is a really nice chart to show that like you can very easily monitor small changes in demagnetization. All right, HBK solutions, and then I'm going to get into my example. So HBK, we offer a product called eDrive. It's a high accuracy power analyzer that records data. We can record electric and mechanical signals, so you can understand that electromechanical interaction. We have the lowest measurement uncertainty, so you can trust those small changes to monitor for turn-to-turn shorts, to monitor for harmonics, to monitor for demagnetization. We have a live view of calculated values, so you can kind of watch these things as they happen. And these calculated values also allow us to not record super high data rates for a very long test. We can just record calculated values. And then when you see an event happen, we can trigger, record that high sample rate data. And I can talk about more of this offline. I don't want to waste this presentation as a sales pitch. And we do have local training and support in most regions around the world. So that's our product. We record a lot of data. We do it very accurately. So here's my example. I made a small dyno out of two. You guys don't give me any of your data, rightfully so. So I have to make my own. So I apologize for my kind of janky dyno. But we have two power drill motors coupled together. In one example, I shove a soldering iron into the winding to cause a turn-to-turn short. And then in another example, I bought a bunch of power drills. I took my lighter to the rotor. I got it extremely hot and pulsed a ton of current at it and demagnetized it. So I have these kind of two examples. I don't have a bearing current example. That one is harder to replicate on your own, especially in this machine. So this is why I had a lighter. So my test procedure, I characterize the healthy motor. I characterize the short circuit. I characterize the demagnetization. You can see here our measurement instrument, my little dyno. I'm just powering it off the drill battery and inverter. I have a fixed load, which is some resistors. Please question my testing methodologies, but I just wanted to show an example of how easy some of these things are to actually monitor. So my test data, I measured and recorded 3 phases of voltage and 3 phases of current. I did not have a torque measurement. I calculated my RMS values, my power and reactive power, my total harmonic distortion, and my zero sequence voltages. And I believe this is my healthy test that I ran. So we just kind of fixed some speeds. We stepped through a variety of speeds to characterize the machine. Did the same thing for the short circuit and the demagnetization. So when I short circuited, when I rammed that soldering iron into the windings, what we saw is that, well, I introduced a pretty drastic failure mode. If we look at the phase currents, my graph on the left, I've plotted my healthy motor, my demagnetized rotor, and then my short circuits. And we can see my healthy and my demag, the phase currents are relatively close together. And my short circuit is just all over. If I look at my zero sequence, we can see much the same. There's a difference between the demag and the healthy, and the short circuit is just all over the place. So it's a pretty drastic thing. You can pick this up pretty easily. The power factor is crazy. But you might say, all right, yeah, you made a really drastic failure. What else can I see? So I don't have a good lead up, but here's an example of time on the X, frequency, so the harmonic spectrum on the Y, and the amplitude is RMS value. So we basically have an FFT as a time series. And we can see in a healthy operation, boom, we have a little bit of switching harmonics. My fundamental is pretty big. And then I have that fault here. And we can see that the harmonic profile gets pretty drastic. So we can start to use the harmonics to maybe predict failures. We can see when a failure happens, and we can immediately see it in the harmonic profile. So there's some pretty useful stuff that you can do with data analysis to understand this, in addition to looking at zero sequence, in addition to looking at power factor. Demagnetization, and I think I'm running a little longer than I expected, but I'm finishing up shortly. For demagnetization, again, I should have taken the short circuit out. We look at the phase voltage. So the demagnetization actually requires more phase voltage to make the same torque. So what we see is my healthy motor is this kind of dark blue trace. And then we do have a notable increase in phase voltage to make the same torque. So because that rotor is weaker, we see this notable increase in phase voltage. And then the short circuit's all over the place. But this is pretty, this is percentage points different. We can make that determination. So that was my phase voltage. If I look at my reactive power, this one I was really fascinated at. Reactive power is kind of the same for a certain area of frequency spectrum. And then my Demag, my healthy motor my healthy motor has less harmonic distortion, and then my Demag has more. So we could also potentially look at reactive power and that phase angle as an indicator. So the conclusion, motors have electrical and magnetic failure modes and degradation. Motor durability can be characterized with electrical measurements, and I highly recommend it because you can understand your system. And HBK offers measurement tools and software for durability, faults, and analysis, and I would be happy to answer any questions with the time we have left. Here's my references. If you want to find me on LinkedIn, please scan this with your phone. I'll give you a second for that. And then thank you much. Please feel free to reach out.
All right, Mitch, I think we'll jump right into questions here.
Cool.
How accurately can torque ripple be measured at high speeds?
Ooh, good question. Depends on how high speed and depends on the motor geometry. So HBK torque sensors have a accuracy of 0.02%, and then a bandwidth of 6 kilohertz. So you can understand at a really high accuracy up to 6-ish kilohertz. So at high speed, it's much more difficult. Then you might be better off with accelerometer-based solutions. I think in the future, we do have higher bandwidth options coming out that might push us up to 10 or 12 kilohertz bandwidth on torque ripple. But it's, yeah, at lower speeds is much easier, and a valid question when you look at field weakening.
All right. Someone's asking if you can go back to your reference slide again, so he has that information for a little bit longer.
Yeah. Oh,
someone's
absolutely.
wondering about ambient temperature also and the effects it might have on demagnification and battery life.
I can't make any comments on battery life. If you're running in a hot environment, and sorry, these slides will be provided to you guys, so I'm not going to linger on this one. So they'll be sent to you. Ambient temperature can just drive the total motor temperature up. So I think that's the big effect. With turn-to-turn shorts, you're obviously worried about what the winding temp is, but that should be in the housing. There should be a cooling system involved. Now, if it's a passively cooled machine, yeah, ambient's a big deal. So I would say if you're within if the ambient's around, the enamel thermal limit or the magnet thermal limit, then yes, big issue. But you're mainly worried about the magnet temperature and the enamel temperature.
All right. Someone's also wondering about cold temperatures and the effect they can have on performance.
There's certain magnet types that don't like the cold. So you might have the same demagnetization effect in a cold situation. As far as the windings and other issues from a fault side, I don't have as much experience with the cold, to be honest. I know there's some magnets that don't like the cold.
We've got time for one more here before we have to close out. What about during a long test? How can you note a sample at a high rate to get more information if something of interest is happening?
Yeah, so with the HBK products, let's say you're monitoring, RMS currents for a certain failure mode. We can actually trigger on, a difference of a certain amount between phases. So in the HBK system, we can monitor a lot of calculated values, trigger on those values, and have a buffer of recorded data for seconds to minutes to even hours in some circumstances. So you can look at a calculated channel, you can trigger based on a difference, and then have data leading up to it for a given period of time. The HBK system's really good at handling large amounts of data.
All right, let's see. Do we have time to sneak in one more, or do we need to? I've got to check with the ChargedEV hosts here.
Unfortunately, we have presentations all day, but we can definitely get you a list of all the questions that we didn't get answered. And we'll make sure Mitch and his team reaches out to you, along with making sure you can get the slides. The link to the slides are in the chat box, and you could also rewatch this presentation on demand and get the slide deck over at the session page. So thank you so much for everyone who attended and your great questions. And thank you, Mitch, for being a part of our conference.
And thank you, everybody. Hopefully to hear from you soon.
Thank you.